Hi, this video is about gases, so we're going to continue on with some gas laws. But up until now, we've kind of been thinking about gases as just a pure gas, and now we're going to think about gases as a mixture of different gases. And so the question is, how do these gases behave when they're in a mixture? So John Dalton said that the total pressure of a mixture of gases is just equal to the sum of the pressure that each gas would exert if that gas were alone. And each single gas's pressure is called its partial pressure. It's part of the total. And so this is Dalton's law of partial pressure, and it looks very simple. It's down here, and you see the T down here means total. The total pressure is just the sum of the individual pressures of all those gases as if they were alone. And this becomes really important when you're doing a lab where you collect a gas over water. And so in this test tube, there's a piece of zinc and it's in some hydrochloric acid, and it'll be a single replacement reaction where hydrogen gas is generated. It's stoppered in the tube, and that hydrogen gas will come up. It will go through this water, and then it's going to displace water here. And so we're saying that our gas is being collected over water. And so when we do an experiment like this, when we collect a gas over water, the total pressure isn't just the pressure of the gas, it also has some pressure from the water vapor. And so that water vapor pressure depends on the temperature. And so you'd have to know the temperature at which you're doing the experiment. And then there are different tables. There's one in the appendix of your textbook that will tell you the vapor pressure of water at different temperatures. And so the total pressure is your gas's pressure along with the vapor pressure of water. And in these ideal gas equations or anything that you're doing, you're going to want to know just the pressure of your gas. And so the pressure of the gas is the total pressure, and then you would subtract from it the vapor pressure of water. So this is where Dalton's law becomes really important in a lab setting. Now, when you do collect a gas over water, you want that pressure of your gas to equal atmospheric pressure. And the way that you do that, so this is kind of just a rough drawing here. So here is our test tube, and it generated some gas, and we collected it over water, and so we've displaced the water. You want the water in your tube or whatever you're collecting your gas in, you want its level to be equal with the water level. And then you can say that the pressure of your collected gas is equal to the atmospheric pressure outside. And so whenever you do an experiment like this, you've collected your gas. Before you measure the volume of gas or whatever you're doing, you are going to want to equal those levels of water, the water inside your test tube or inside your graduated cylinder with the level of the water inside, like the water bath that you're doing the experiment. And then you can say that the pressure of our gas is equal to atmospheric pressure. All right, well, let's look at the ideal gas equation with mixtures of gases. All right, so if you wanted the pressure of, like, say, gas 1, it would be equal to the moles of that gas times RT divided by V. If you wanted the pressure of gas 2, so a different gas, it would be the moles of gas 2 times RT divided by V. But if those two gases are at the very same temperature and volume, we could say this: the pressure, the total pressure, is equal to the total pressure of moles times RT divided by V. And that's pretty useful when you have a mixture of gases if they're at the same temperature and the same volume. All right, now there's something called mole fractions, and we've not talked about it yet. Mole fraction is just as it sounds. If it's given by a Greek letter chi, so here it is, and that is the mole fraction of gas 1 is equal to the moles of gas 1 divided by the total number of moles. And so this has no units at all, it's just how many moles of your gas over the total moles. And so let's have a look here. P1, we saw in the last slide, is equal to N1 RT divided by V, and here's a total pressure equation. If we are at the same temperature and volume, if we divided these two equations, the RT and V would cancel, and we'd be left with P1 over PT is equal to N1 over NT. And this is the mole fraction. So we can say that the pressure of gas 1 in the mixture is equal to its mole fraction times the total pressure. And so this is a very useful equation to use when you know the moles of different gases that you have, or if you know the total pressure or things like that. And we're going to practice a lot with these equations. All right, well, have a good night.